Welcome to the module. So, now we will see the setup, and what we do is that we will slowly increase the voltages at a step of 0.5 and we will observe at what frequency the encoder is rotating. So, before doing that, let us see the connections. So, what I have done here is that we have total 4 supply. So, this case this particular RPS has total 3. So, the middle part, if you observe, it has plus 15 dedicated plus 15 and minus 15 channel here, this particular portion. So, for powering the op amp, we are using plus 15 the red one and the minus 15 the green one with a common ground black, whereas this particular channel we are giving to power transistor, and this channel we are powering encoder. So, whereas the input to the positive terminal is powered by using this particular power supply. So, in this case we are using this particular channel, the first channel. So, here you can see the channel 1, the channel 2 is off, but the output is also on right now, but the output is the output from this channel is 0, this is channel 1. So, what we are doing is that this one we have given as an input to the positive terminal of an operational amplifier. So, if you see, this is a transistor which we are using 2N3019, which is NPN transistor, and this is our 56 ohm resistor which is connected in series with in between the emitter of the transistor to the input of a motor, such that it will allow it will not allow higher current to pass through the motor. Similarly, here if you see, this is a TL072, again we are using TL072 in negative feedback amplification mode, basically an inverting mode. So, that the voltage that is being applied at the input of a positive terminal will be generated across the output of motor. As a result, whatever the output the controller is giving, the same output will be across the motor, but the current required to drive the motor will be taken from this transistor, and the output of this, the output of the operational amplifier is connected to the base of transistor by using the another resistor here, which is 180 ohms to 220 ohms. The only idea of having this resistor is to limit the current flow through the transistor. This is the motor that I was discussing about. This is our micro gauge motor, and the back side if you see, it has encoders connected to this. Now, if you see the pin configurations of this DC motor, the top one is the motor input, the bottom which is connected to the red wire M2, which indicates with an M2 is a other terminal of the motor input. So, whereas the second pin is a ground, the second pin here is the ground, and the C1 C2 are nothing but the inputs to the outputs from the encoder. So, in order to understand whether the motor is rotating in clockwise direction or anti-clockwise direction, by observing the phase shift between C1 and C2, we can estimate the rotation of the motor, and the RPM will be determined based upon how many number of pulses the encoder is giving per minute. The fifth terminal is VCC, which is nothing but the power to the encoder. So, basically the max input voltage given to the encoder is 5 volts, and the motor will be the maximum voltage that is required for the motor to operate is of somewhere around 6 volts. So, now along with this, it also has other signal conditioning circuits which I will be discussing in next coming sessions. Now, to the CRO, one input is connected to the CRO, one channel, the first channel is connected to the first channel of this voltage, which is nothing but the input voltage that we are giving it to operational amplifier, whereas the other channel, the channel 2, it is being connected to the output of the encoder, but the channel 2 grounds are completely separated. The reason is that in next case we require to have a negative triggering pulses. Because of that, in the digital pulses that we see at this point will be always 5 to 0, not to 0 to 5, it will be 0 to minus 5 because of that shifting. So, now what we do is that we will apply input voltage of 1 volt. So, here we can see I am slowly increasing the voltage. So apply the input voltage of 1 volt, and here we can see the pulses, right. So the yellow line corresponds to the input voltage, which by using the channel 1 RPS that we are doing. The blue line indicates the output from the encoder pulses. The reason why we are getting 0 to -5 volts is because of our shifting. We have made reverse connections at the output of the encoder for the future purpose. I will let you know why exactly. So it is being powered with the 1 volt right now, right. So in order to understand how many number of pulses the RPM of a motor, what we have to see is that we have to count how many number of pulses that we are getting per minute. But right now the scale is at somewhere around 10 millisecond scale, and if we count, we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 pulses, approximately 21 pulses in total of 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks. Each block correspond to 10 millisecond. So that means for 90 millisecond we are getting 21 pulses. 90 millisecond we are getting 21 pulses, which means that if I want to calculate per minute, so it will be 60 into 21 divided by 90 millisecond. So which will be 1400 pulses. Okay. So one thing it is clear that by looking into how many number of pulses that we are getting, either we can compute in terms of an RPM, or rather than that we can also notice the frequency at which it is coming. So when you look into the frequency, we are getting approximately of 235 hertz. So one way is by looking into the how many number of pulses, or another way of looking is by looking into the frequency. So right now the blue color one is enabled with the frequency. So it shows somewhere around 227 hertz. So that means one thing we clear that for 1 volt we are getting 227. Hertz. So we will change it to 1.5 and we will see. So right now it is on 1, I am slowly changing to 1.5. So I have powered with 1.5. Now if I see the frequency at the output side, it is 357. So 357 hertz. You can also notice the motor is rotating. So for 1.5 it is 357 hertz. Now I will increase to 2 volts. Right. Now the frequency is 515 hertz. So for 2 it is 515. So slowly I am increasing for every value. So 2.5, 668, then 3, 827. So we can easily understand that it is the voltages are the frequency is slowly increasing. So we will observe. Now I will go with 3.5. You can hear the noise. Now the frequency is 989 hertz. So I will go to 4 volts. .1157, then 4.5, when I see the value, it is 1.31 K, this is K, this is kilohertz, then I will go with 5. So it is rotating at a maximum RPM, this is operated at 6 volts. So right now for 5 volts it is 1.48 kilohertz, 1.483 kilo. So we understood the frequency, but until unless we plot it on Excel or we plot a line graph, we cannot understand whether it is linear or not. So what I will do is that I will open an Excel. So I will enter the values. Now, so since I have to do f by 14, what I will do is that this divided by 14, this is the hertz. So at 5 volts, it is clear that it is rotating at 105, 106 approximately RPM. So we also know that the maximum RPM it can rotate is 155 RPM. Now we will plot a graph between both frequency and the input voltage as well as RPM versus input voltage. So this is RPM. So I will select these two, insert, this is one graph. So one thing, for 0 it should be 0, so I will insert one more for 0, 0 hertz and 0 RPM. Okay. So let me rewrite, okay, let me plot for everything. Okay. Now I will also insert a trend line to understand whether it is straight or not. Okay, almost same. So let me see the more options here. Then I will go with display equation on chart. So for frequency it is showing somewhere around 303. So for every voltage it is changing a frequency of 300 approximately 300 hertz. Now if I plot with respect to the RPM, so what I will do is that I will go with, I will add new sequence, select data. So this I rename it as frequency versus Vin. So I will add new sequence which is RPM versus Vin. So the sequence, X sequence is this particular value, whereas Y sequence is this value. Now when I see the graph, I got, but I do not know because of this magnitudes are really higher. So what I will do is that I will take another chart and I will plot it on that. So this versus this I want. I will go to insert, I will go to new chart, yes. So this is RPM chart as well as this is frequency chart. So both curves look similar, of course it should look similar. Now I will add thread line to this, I will go to the more options, then make Okay. So, I am selecting the thread line, going to more options, display R value as well as the equation. So, one thing it is clear that even though it is approximately not linear, but the linearity error is very small, one thing it is clear that R square value is really higher. So, we can consider it as a linear, and the y value is we are getting somewhere around 20.3 approximately. Since if we are considering the offset as 0, intercept as offset as 0, so the change in RPM value is 20. So, which means that for every 1 volt we will get approximate RPM of 20 plus or minus 10%. So, one thing it is clear, the sensitivity factor of this sensitivity factor is 20 RPM per volt approximately. So, from the graph it is clear 20 RPM per 1 volt is the sensitivity factor. So, with this understanding we know that we will go with the same sensitivity factor as 20 RPM per 1 volt, but system will not understand 1 volt whether 1 volt is 20 RPM or 100 RPM, but this is only for our reference. But system what will it will try to understand is that whether the feedback signal is also 1 volt or not. It look for the system input value magnitude is matching with the system output magnitude, provided these two should be of same units. So, for that in order to have the same units we are saying 1 volt is corresponds to 20 RPM approximately, right. So, this particular block is done, driver part of the DC motor and the working with this is done. Now, the major part is designing a sensor signal conditioning circuit, right, and interfacing the output of a DC motor to sensor signal conditioning circuit. So, one thing it is clear that for 1 volt we are getting 20 RPM. So, this part is clear. So, let me make it to 0. Okay, I made to 0. Now, the next step, implementation of signal conditioning. Why do we require? Now, it is clear that whatever the input that we see in the CRO is completely in the pulsating. So, we are getting, generally speaking, we should get from 0 to 5 volts, but in this case when we observe into the CRO we are getting 0 to minus 5 volts. The reason is that the clock pins, we have reversed the clock pins. So, if you see the connections of a motor which we have already seen, we know that we have for the encoder we have a different values V1, VCC, ground as well as C1 and C2. So, what we have done is that we have done VCC connected with 5 volts ground to ground, but instead of C1 connecting it to CRO, we made this particular part to ground and this particular part we have connected to CRO. As a result, we will see a reverse signal image 180 degree phase image of the signal or flip signal of the actual signal. Why we have connected, we will come back to the next one, why it is required. So, that is why the CRO output it is shown as 0 to minus 5 volt, but frequency remains same. What changes is duty cycle. The next part, what we have to observe, how exactly we convert this digital pulses into analog signal with same scaling factor as 1 volt per 20 RPM, 20 RPM per 1 volt, the same scaling factor. How do we do that? So, for that the only idea is that by using one monostable multivibrator and integrator. So, why do we require a monostable multivibrator? The reason is that in this particular case, based upon change in the RPM, the frequency of the signal is keep on varying it, right. And moreover, since it is based upon number of pulses, and when you look into the working of our encoder, it is based upon how much time duration that particular wheel or toothed wheel or is in contact with respect to the Hall effect sensor gives this duration of time, which means that the pulse width of the PWM signal entirely depends upon the RPM2, which is not constant. But if I make, by using a monostable multivibrator, if I maintain a fixed duty cycle or a fixed on time pulse such that whenever the RPM is changing, the number of such pulses are also higher, but this pulse width will always remains constant. If I maintain, then integrating over a period of time gives you the average output voltage. And moreover, if the motor is rotating with an higher RPM, the number of pulses that we are also getting will also be higher. As a result, the more number of on time signals we observe and the integration output will be higher, right. So, with that understanding we have designed a monostable multivibrator and an practical integrator. Recall the working of a monostable multivibrator, also the working of a practical integrator. I will also explain why exactly we are using inverting amplifier here, but just recall our previous lectures about the understanding of a monostable multivibrator as well as understanding of practical integrator. Now, so the complete purpose of going with a monostable multivibrator is to provide a fixed duration pulses, right, to provide a fixed duration of on time. But how do we generate it? On what basis we select this is the fixed duration, right. So, in order to understand that, one thing what we have to know is that at a higher voltage, higher working voltage in this case. So, in this case the higher working voltage is 5 volts. What is the minimum pulse width that we are getting from the encoder, and what is the total time that you are getting if you know, and if you make the monostable multivibrator output, the pulse width should be smaller than this particular value, right. As a result we will generate a pulse and we can design a monostable multivibrator for that particular. What I mean to say is that, so what we have done is, for different input voltages we have observed the on time as well as an off time from 1 volt to 5 volt with a step of 0.5 itself. So, one thing it is clear that when we are operating at 1 volt, the on time is 2.7 millisecond, off time is 1.2 millisecond. So, total put together 3.9 milliseconds and the frequency is 256. So, which is corresponds to the same what we have also seen in our previous recording experiment. Now, when we see, as the voltages keep on increasing, the frequency is also increasing, which means that on time and off time values are decreasing because the frequency is inverse of time. So, when we want to design a monostable multivibrator, the on time, the charging time of the capacitor as well as the discharging time of the capacitor should be smaller than that of the on time and off time of encoder. So, in order to understand to what particular T1 on time the monostable multivibrator has to be designed, we have to look for on time and off time of the lower on time and off time values of encoder. So, when we look into this table, it shows that under 5 volts we are getting a 430 microseconds of on time and 200 microseconds of off time, and total time of single pulse is 0.63. What I mean is that when we look into encoder output signal at 5 volts, because only at the 5 volts we will get a lower value, low time value, this particular time is 430 micro and this particular value is 200 micro. So, the total time, single time is 630 microseconds, that corresponds to 1587 hertz. So, what we also got is approximately of 1.48 approximately the same. So, whatever we are planning to design the monostable multivibrator, the on time should be smaller than that of the the on time of encoder. So that what happens if it is higher? If the on time of the monostable multivibrator is higher, at that particular frequency there are chances of missing the pulses, right. So, because of that reason we have to consider the on time of a monostable multivibrator should be smaller than that of the on time of this pulse, right. So, in this case if you see the total pulse on time is here is 430 microsecond. So, the T1, the on time of monostable multivibrator should also be less than 430 microsecond. Not only that, another important factors that you have to consider when you are designing a monostable multivibrator is whether enough charging of a capacitor enough charging time of a capacitor. So, this tells us about the discharging time of a capacitor, and enough charging when during this time whether we have enough time for the capacitor to go to 0.7. So, before understanding that, just recall the working of a monostable multivibrator. So, this particular block, if you consider, this particular block is completely differentiator, right. So, C and R corresponds to differentiator, and this diode. So, when we give a clock pulse signal at the input of this particular portion, here we get spikes. Wherever you have a positive, you will get a positive spike, wherever you have a negative, you will get a negative spikes like this. But for monostable multivibrator to work, we require only a negative spike. Why do we need only a negative spike? We will come to that. So, in order to have only a negative spike, by passing through the diode in a reverse in this configuration that we see. So, only during the negative time the diode D3 will be in a forward bias condition. As a result, this particular peaks will be eliminated. Finally, you will get this way at this particular point. But why do we need it? Now, if you recall the working of a monostable multivibrator, so we have capacitor C1, we have diode D1, we have R1, and R3 and R4 corresponds to our beta, right. So, how does it work? Initially, if you consider, so since it is extension of your Schmitt trigger, we know that we always have a positive feedback in this case. So, because of the positive feedback, the operational amplifier will always either go at plus VCC state or minus VCC state. Imagine right now the output is at minus VCC state. So, what happens through this R1 and capacitor C1, this capacitor starts charging. If I do not have this particular diode, it is supposed to charge till beta VCC plus beta VCC, but because of the diode, when this capacitor voltage is greater than 0.7 or Vd, the cut in voltage of a diode, then the diode will be in a forward bias condition and it will not allow the capacitor to charge more than 0.7. That is nothing but the capacitor charging voltage. So, here we can see from here. So, initially when it is at plus VCC state, I made it in ulta. So, whenever it is in plus VCC state, the capacitor starts charging and it goes to plus VCC state. So, whenever it is supposed to go to beta plus VCC, but because of this diode, this cannot go more than 0.7 volts. So, it will stop charging at 0.7 volt, right. So, this region is called stable state, right, because until unless this voltage is greater than this particular voltage, this value will be always plus VCC. The reason is that when you see the voltage here, so 10 kilo on 4.k and here it will be 15 volts plus VCC, meaning if it is powered at plus 1 minus 15. So, this voltage is always restricted to 0.7 volt, this voltage is higher than, so say this is V2, say this is V1, In this case V1 is 0.7 volt and V2 is higher than V1. So, it will be always in plus VCC state until V2 becomes lower than that of V1. So, if I want to make V1 state, if I want to go to the next state which is an unstable state, which is a fixed duration state. So, that means output to go to minus VCC. So, then V2 has to be provided with a smaller voltage than that of V1, but how do we provide it? So, in this case it is not possible. So, since it is not possible, what we can do is that if I can make at this point provide some negative triggering pulse. If I can provide a negative triggering pulse at V2 terminal, as a result, since it is a negative smaller duration triggering pulse, this particular voltage at that moment will be smaller than V2, because say this is minus 5 volt. So, this is 0.7, this particular voltage, this is minus 5 for particular duration. As a result, this goes to minus VCC state now. So, since the output is minus VCC, then the capacitor starts discharging. So, right now you are in this stage, it starts discharging till what time? Till it reaches to minus beta into VCC, right. So, the complete calculation of a monostable multivibrator as well as a stable multivibrator working experiment we have already seen in the previous course. You can just look into that, but I hope now it is clear that if you understand that it will discharge only for particular time duration, and this particular time duration entirely depends upon what is an R, what is a C1 and your R3, R4 too, right. So, this tells you how fast your capacitor will start charging, right, and this R3, R4 tells you till what value the capacitor will go up to. So, that minus VCC into beta. So, even the minus voltage that we are providing, the VCC that we are providing is also very much important in this case too, right. So, this state where it goes to minus VCC and at one particular point the capacitor value will be higher than that of minus VCC value, then it goes to the next state which is nothing but stable state. So, this duration is nothing but unstable state and the duration of this entirely depends upon R1 and C1, right. How do we design it? So, in this case if you observe, we have to design the same pulse, but the duration of this should be smaller than 430 microseconds and the complete cycle should be lesser than 0.630 millisecond, since it is 0.630 millisecond or 630 microsecond. So, that means if I know the formulas related to that, right, it is easy for me to do that. But now it is clear that why we require to design less than 430 microsecond, because if the pulse is if the on time pulse of this is greater than 430 microsecond, there is a chance when the motor is rotating at a higher RPM, at one particular moment there are chances of missing few pulses, right. So, in order to not to change the accuracy of the system, we will be limiting to less than 430 microseconds. And another reason why the complete charging and discharging of complete pulse should be less than 630 microsecond, because for the capacitor to charge also requires some time, right, and that time the complete discharging and plus charging time should be within the range of 630 microsecond. So, when you look into the equations relevant to the monostable multivibrator, now if you see this is R4 and R3, based upon that we have considered beta. So, the beta is nothing but 0.32. So, this is not 0.5, this is if we consider R3 and R4 as either 10K or 4.7K, then beta would have been 5 volts 0.5, but in this case we have considered different beta different R4 and R3 resistors. So, the value is 0.3. Now, so for the designed calculation R1 and C1, if I see the time discharge, the formula for that is R1 C1 into log 1 plus R4 by R3. So, if you see that the value will be 280 approximately of 280 microsecond. So, if you see this is 430 microsecond, but the pulse that we are getting is 280 microsecond, which is smaller than 430. So, one particular design criteria is met, right. Other one, the charging, the total time should be smaller than 630 micro. So, if I want to understand the total time, I also want to know what is the time for a capacitor to charge, right, because before this signal I should not get any, I should not get a next pulse, next encoder pulse. So, because of that we also have to see what is the time taken for the capacitor to charge. If you miss this particular charging time, there are chances of getting errors because of because you are not providing enough time for the capacitor to charge it. So, when we calculate the capacitor charging time, which is nothing but R1 C1 log 1 plus beta by 1 minus Vd into Vcc, where Vd is nothing but the cut in voltage of the diode that we are considering it here, right, as well as Vcc, what is the power supply that you are considering. So, when you substitute all the values, so we are taking IN 1007, we can calculate it as approximately of 240 microseconds, right. So, the total time, which is nothing but discharging time as well as charging time, is 516 microsecond. But what is the room that we have with a higher RPM, when we are rotating at 5 volts, we have a room up to 630 microseconds, right. But here in this case we require a total of 516 microseconds, which is smaller than that of 630 microseconds. So, this the whatever we have designed, the particular resistance that we have chosen R1, C1, R3, R4 is good enough in order to not to miss any pulse, which means that it can count for all the pulses, right. It will not miss anything. So, the accuracy will be good enough. So, I hope this is clear. So, these particular resistors and capacitors have been selected by doing different permutations and combinations here. So, we have done, here we can observe the different set of values that we have tried in order to match with our requirement. So, we have gone with different capacitors, different resistors, and we have seen what is an on time for each capacitor, whether everything is within our limit or not. By adding these two, whether these are within our limit or not. Okay. So, we have done different calculations in order to match the resistance and capacitance value. So, finally, we have come out with R as 3.3 kilo and capacitor as 22 microfarad, which is meeting our requirement, right. So, and another important thing what we have to do is that whatever the differentiator time period that we are considering should be the pulse duration of the differentiator circuit, which is nothing but this particular circuit, this particular triggering pulse should be 10%, minimum of 10% of the input pulse. So, in this case the input pulse is somewhere around 280 microseconds. So, 280 microsecond into 10%, approximately of 28 microseconds of pulse we require. So, by using this particular resistor, by fixing this particular 10 nanofarad capacitor, by varying this resistor, we are achieving the pulses that we require. So, I hope now it is clear why we are using the negative pulse at this point. Instead of doing 0 to 5 volts, we are giving minus 0 to minus 5 volts. The reason is that we require only the negative spike, we do not need any positive spike. So, in order to get this negative spike, the triggering input provided should be always 0 to minus 5 volts, otherwise all the spikes will be greater than that. So, for that intention we reversed the output of the encoder. Instead of measuring with respect to the ground, we measured everything with respect to 5 volts, so that the output will be 0 to minus 5 volts. So, I hope this is clear right now.